We're very happy to have you with us. There are more and more people joining, so we'll need wait for, I guess, for 5 minutes before we can get started. Admit all. Hi, for those of you who just joined, feel free to write in the chat and tell us where you're calling from, where you found about this event, and what brings you here. Hello. Oh, nice, from India. So we have people from many different continents. Okay, more people trying to join. Wait, I'm gonna let you. Hey, Bill. Happy to have you with us.
Hey there.
Hello. Toronto. Oh, yeah, that's your mark. Yes, you've got a few people from the UK, be following the meetup then. Be interested in Python and machine learning. Perfect. Alteryx, yeah, that's a popular tool, even though I personally prefer to write my own code. Okay, 34 participants. Let's wait for a few more minutes. Okay, more people coming. One person every 5 seconds, which is absolutely great. Okay, more people joining. Now we're at 45. 45, perfect. Six, we're getting close to 50 participants. Okay, 49, getting there. And 49 again. And 15, perfect. For those of you who just joined us, feel free to share with us where you're calling from, how you learned about this event, and what brings you to the session. We might understand we have people from all over the world, and it looks like everyone is interested in data science. So very, very happy to hear about this. Okay, I guess we can start in a couple of minutes. There are still people joining. Yeah, I guess we have to start, so we're scheduled. Yeah, here's another person. Okay, let me share my screen. Okay, 3 more people. And I guess we can start. So let me share my screen. All right. So welcome everyone. Thanks for being here with us. This event organized by Beyond Machine and Data Science London, one of the biggest data science communities in Europe, organizing events online for now and hopefully returning to in-person events within 2022. So a few words before we start, who we are, why we do what we do, housekeeping rules. So Beyond Machine's mission is to help anyone get a job in technology. We're mostly focused on data science. We organize many community events, free workshops, etc. Feel free to check out our website. This is still like a new initiative. So if you're interested in the theme of data science, entrepreneurship, how to get a career in technology, feel free to just write to me directly. And talking about myself, you can call me Stelios. I've been in the area of technology for pretty much all my career. My own expertise is first and foremost in data science, and I also do some work in the space of blockchain, more specifically tokenomics. I've written a book on the topic of data science. It's a very introductory textbook for anyone who wants to learn more about the topic. More than happy to share a copy with you if you want to send me an email. And I'm also affiliated with universities like London Business School, UCL, and Cambridge University. But I spend most of my time actually as a data scientist or an advisor for various startup companies. And the reason we created Beyond Machine, the reason I'm organizing Data Science for London, Data Science London, is because I'm very passionate about data science, as you can imagine. And we love having some great speakers with us. Like Mark today, who's written a book on deep learning with structured data. Based on the registrations, the number of registrations we've seen and the number of attendees today. This is clearly a very interesting and very important topic. I'd say that the majority of data in the real world is structured, but apparently deep learning is often ignored as a potential solution to analyze this data. So that's why Mark wrote this book, and I'm going to be sharing a link to his book on the chat. Just before I hand over to Mark, I'll be the moderator for regarding any questions. As you can see, there are many people and more people joining us. So if you have a question, please write into the chat, and then we'll deal with this towards the end of our session. So that's it for me. And now I'm going to mute myself and let Ryan share his screen.
Thank you so much, Stelios. I really appreciate the opportunity to speak to everybody today, and hopefully this will be a useful session. I think, like you said, this is a topic that has not received enough attention in the world of deep learning. So hopefully this will be a useful session. I do encourage you to ask questions. So make it as interactive as possible. And you just confirm whether you can see my screen now.
All good.
Okay, great. So I'm going to be talking, and we'll just go very quickly over what my background is. I'll talk about what structured data is and why we might want to apply deep learning to it. And then I'm going to go through the end-to-end approach that's covered in the book that Stelios mentioned. How we clean up the data set, how we build and train a deep learning model, and how we deploy that model. Then I'll talk a little bit about some future enhancements to this topic, and then go into some resources. If you're interested in learning more about this topic, some additional resources on top of what's covered in my book. So my background, I spent a large part of my career working at IBM. I was a manager in the DB2 relational database area. So DB2 is IBM's marquee relational database system. And towards the end of my time at IBM, I worked in the Watson area on Watson Studio, which is IBM's environment for doing data science. After that, I was a data science manager with Intact Insurance in the data lab in Toronto. And there I worked on an application that allowed auto insurance clients to get a rebate on what they paid for auto insurance based on how they drive. So the team that I worked with trained a model that would predict somebody's future claim behavior, that is, whether they would have an accident and make a claim based on their current driving behavior. And the driving behavior was collected from an app running on people's mobile phones. I recently started working at Google. I'm currently a manager there of a technical writing team in their cloud, AI, and industry solutions area. But today I'll be speaking as a private citizen. So any opinions you hear, and I will have some opinions, they're my own. They don't represent that of my current employer or any of my former employers. So the first thing we look at the topic of deep learning with structured data. The first question to answer is, what is structured data? And for the purposes of this discussion today, it's simply data that's in a tabular format. That is, it's in rows and columns. And this could appear in a relational database, a table in a relational database, or something as simple as a CSV file or an Excel file, a spreadsheet. You can contrast this with unstructured data or non-tabular data, such as images, audio, and freeform text. Now, that kind of data does have a structure to it. And in fact, with the publisher of the book, we went through some back and forth about whether we should call it deep learning with tabular data. And if I had a time machine, I'd go back and I would change the title to deep learning with tabular data, because it does cause a little bit of confusion. People will say, well, there are other kinds of structured data in addition to tabular data. And that's a valid point. But in this discussion today and in the content in my book, it's about data that's organized in rows and columns. So if you look at all of the data in the world, all of the digitized data in the world, this is from a survey done in 2019, only about 20% of it is structured data. So the vast majority of it is unstructured data. So why does it matter to look at structured data if it's that small a proportion? I think there are two reasons for it. The first is, in our modern lives, just going about your life as a citizen, as a customer, as an employee, as somebody working with any kind of organization, in the course of the day, just doing what you do, you're probably updating data in hundreds, if not thousands, of tables. So what that means is that the bedrock of large parts of our society runs on structured data. Look at any insurance company, any bank, large number of government organizations at any level, municipal, provincial or state, national, nonprofit organizations are using structured data to manage the most important parts of what they do. So that's one reason why structured data is important. The other reason is, and this is something that I found kind of frustrating when I started to learn about deep learning, is a lot of us spend our days working with structured data. That is, where our jobs don't involve dealing with images or audio or maybe free-form text. For some people it does, but for a lot of us, the kind of data we're dealing with is data in tables. So for those two reasons, structured data is important. And the idea is, can we use deep learning on it? So if you look at deep learning over the last 10 years, and really when people talk about artificial intelligence today and the impact it's had, a lot of time what they're really talking about is deep learning. And while the ideas of deep learning have been around for decades, and they had their origin in the 50s, and people had some early successes with it in the late 80s and the 90s, it's really less than 10 years that it's become something that's had widespread attention and adoption. This is going back to the ImageNet contest in 2012, where a team led by Jeff Hinton from the University of Toronto had results that were extraordinary compared to any of the other competitors. And this got a lot of attention over that time. And all I'm showing on this page is, and this is biased, these are things I think are particularly important, but deep learning has really been making headlines, literally making headlines across a number of different kinds of data. And there are examples here of deep learning having an impact with image data, with text data, with various different kinds of data. Most recently in 2021, OpenAI's DALL-E creating images from text, that is giving text input, generating an image, and OpenAI's Codex being able to generate code from English language descriptions or translate between different kinds of code, GPT-3. There are all kinds of remarkable accomplishments that have been done with deep learning or systems that incorporate deep learning across a wide variety of different data types, but not with structured data. And really, the question is, and hopefully people are asking the question, people who have come to this session today are asking that question, why is that the case? If deep learning has had such a revolution, it's been revolutionary with other kinds of problems, then how come it hasn't had that same impact with structured data? And I think there are a number of reasons to that. Some of them are technical and some of them are organizational, societal, just the way that people react to things.
Sorry, Mark, some people are asking
Sure.
whether you're sharing the wrong screen because it looks like the slides are not moving forward.
Okay, so are you just seeing the introductory screen right now?
Yeah, slide 1.
Okay, let me see if I can. I'm going to stop sharing and start sharing again. Hopefully that will.
Yeah, sure. I mean, there are also
Okay,
still people joining, so that's fine. I mean, this was just the introduction, so we still have time. Now we're at 65 participants, which is great.
Great.
Okay, maybe you want to go quickly from slide 2 to 5, up to you, because I think everyone was just left at slide 1.
Okay, so can you see the what is structured data slide now?
Now we're slide 5. Deep learning has had a huge impact. That's what we see.
Okay, you see this? Okay. It sounds like there's a bit of latency catching up. So what I've done is I've stopped sharing and started sharing again.
Yeah, sometimes if you share full screen, it can also Zoom can mess things up. This can happen.
Okay.
But yeah, right now we're seeing screen 5. Deep learning has had a huge impact.
Okay. Can you see, but not with structured data?
No.
Okay. So what I'm going to do is I'm going to get out of presentation mode and see if that puts a little bit less load on things. It's not going to look as pretty, but hopefully people will be able to still see it.
Yeah, that's fine. I've had some problems with this in the past as well.
Okay.
So
How
now
about,
we're on slide 5, slide 6.
do you see slide 6 now, but not with structured data?
Yeah.
Okay,
Yeah.
great.
People are asking
Okay.
whether they can also get access to the PowerPoint after the presentation.
Sure. Yeah. So Stylianos, I sent you the PDF. For,
Yep.
So
Actually,
you can share that.
yeah.
Feel free to share that with everybody.
Perfect. Okay. Cool. So I'm going to mute just to confirm we're seeing slide 6 that says,
Great.
but not with structured data.
Okay. Fantastic.
Perfect.
And do let me know if it gets stuck again. Thank you.
Great. Thanks.
All right. So like I was saying, there's been a huge impact of deep learning on a number of different kinds of data, but not with structured data. And I think there are a couple of reasons for that, or several reasons for that. The first is there hasn't been a publicly available headline, like literally a headline. You've seen on the previous page the headlines for other kinds of data that have been accomplished with deep learning. And that just hasn't happened yet with structured data. Now, part of the reason for this is for the other things that I'm going to be talking about. The other is some of the accomplishments that have been happening with deep learning with structured data have been, like I like to say, behind the firewall. That is, they're part of a particular company's competitive advantage that they have. So there have been some significant accomplishments, for example, with fraud detection or as other aspects of financial services. But these data sets can't be shared publicly. There's extremely sensitive private information involved in them. And the work that the companies have done constitutes a significant competitive advantage that these companies have. So the point is, while there may be some significant accomplishments that could be headline worthy, they're not the kinds of things that the companies that have made them feel free to be completely public about. Another reason is that transfer learning for structured data is not solved. So by transfer learning, I mean you can train a model on the ImageNet data set, for example, with millions of images, and then use that model, fine tune it in a topic area that has maybe a very small number, a relatively smaller number of images, such as detecting certain kinds of sea mammals from aerial photographs, and take advantage of all the training that was done on a general data set and still be able to specialize it to a particular specific use case. So transfer learning has been very powerful in the area of image data and text data, but it's not a problem that's been solved with structured data. And I don't know whether it's say yet, or if there were fundamental blocks to be able to actually take advantage of the transfer learning with structured data. But right now, any of the research I've seen, this isn't a problem that's been solved. And speaking of research, there has been limited, compared to some of the thousands of papers and theses being written, applying deep learning to other kinds of data, it's been fairly limited research interest with structured data. And this could be a chicken or egg thing. It could be that researchers want to spend their time where they feel like there's attention, where they feel like their work is going to get recognized. And it could be that somebody needs to make a breakthrough first before people want to invest their academic and their research careers in this. That doesn't mean there isn't any interest. And in fact, in the summer of 2021, there was sort of a spurt of papers about the topic of deep learning with structured data. And I'll link at the end of this presentation to a summary of those papers. So there is definitely some interest, but I don't think, in my personal opinion, I don't think that it's commensurate with the potential that applying deep learning to structured data actually has. And then finally, there are non-deep learning methods like XGBoost that already do quite well with structured data. So there's a certain aspect of if it ain't broke, don't fix it. Now, I don't know if anybody knows what the picture on this page, what that is. Anybody have a guess? I'm going to put into the chat of what that thing is in the picture. It's a rotary engine. That's right. Very good. So if you look at the history of rotary engines or Wankel engines, this is an idea that there's certain advantages to rotary engines: smooth delivery of power. They're simpler. There are fewer things to break. But if you look at over the last 50 years where they've been used, so Mazda based their business on rotary engines for a while. You know, the RX-7 and RX-8 had rotary engines, but they just weren't, the benefits of rotary engines just weren't compelling enough to overcome the dominance of piston engines, at least prior to the advent of electric cars. So they've been a bit of a sidelight. There are advantages there, but the advantages weren't to the point that they could overcome the engineering effort that was put into piston engines. So deep learning with structured data does run the risk of being the rotary engine of the deep learning world. And that may be because the differences between deep learning with structured data compared to XGBoost just aren't significant enough, benefits aren't significant enough to attract the kind of research investment to really make them better, or that the advantages just aren't compelling enough for people to sort of take it seriously. So I want to talk a little bit more about the objections that people have to deep learning with structured data. And there are three that are in particular that I address in the book. And the first two I don't think are all that valid anymore, but the third one is important. So the first one is deep learning is more complicated than non-deep learning methods. So why take an approach that's more complicated when you do something simply? And I think this objection held more water if you go back 5 years, but there have been huge improvements in the simplicity and the accessibility of deep learning frameworks. So in particular, in 2019, when Keras was the high-level API for deep learning that sits on top of TensorFlow, when it was kind of integrated into the TensorFlow ecosystem, that made the TensorFlow ecosystem more accessible. And then there's Fastai, which I'll talk more about a little bit later, where you have something that's really tuned at making deep learning as simple as possible for developers, for non-specialists to use and to apply to their areas of expertise. So I think that this objection really isn't as significant as it was before. The second objection is a bit surprising, which is that structured data sets are too small. Now, I know from having worked in the relational database area and working with real clients for DB2, it's quite common for people to have tables that have 1 billion or more records. So there are huge structured data sets. I think where the issue comes here is where you see contests in Kaggle, for example. The structured data sets, that is the publicly available open source data sets, will tend to be smaller. And for deep learning to have a good chance of success, you need to be into, as a rule of thumb, either the high tens of thousands or the hundreds of thousands of records. So it doesn't tend to work very well with a data set that's smaller than that. So I really think this objection is more about easily accessible open source data sets, commonly being smaller for structured data than for non-structured data. But in general, in terms of business problems, in terms of real world problems, I don't think that this objection holds any water. The third objection is a tough one. And XGBoost is a non-deep learning approach, or non-deep learning machine learning approach that's been extremely successful in winning Kaggle competitions involving structured data. So it'll tend to be the default choice, the go-to for people who are looking at trying to solve a problem that involves structured data. And this is just a fact. I'm going to talk a bit more about a section in the book where I go through comparing deep learning implementation to an XGBoost implementation. And XGBoost does have some limitations in itself, but this is kind of getting back to what I had on the last page. If you compare a rotary engine to a piston engine, if you're going to make a decision to invest in a rotary engine, it needs to have some really strong benefits. It can't just be about the same. It needs to have some strong benefits in order to knock out the incumbent, which in this case is XGBoost. So with this background and my interest in structured data, my interest in deep learning, I wanted to write a book that would cover this topic. And the goals of this book, the first are to make an argument for using deep learning as an option for solving problems involving structured data. So problems where the data is in a relational database table, in a CSV file in a spreadsheet. And I'm not making the argument that we should be using deep learning all the time, but we should have an open mind about it, because there certainly are situations where deep learning makes sense for structured data. The other thing I wanted to do was show a complete end-to-end solution built around a deep learning model, starting with a real-world data set, then going through all of the individual steps with an open source stack, and ending up with deployment of the model. So showing this complete. Another deficiency that I saw in some of the education about deep learning is that it will tend to focus on, let's get the model trained, and not really cover the idea of, well, once the model's trained, how do you actually make it useful? How do you deploy it in a web application, for example? So the first thing I needed to do was find a problem to tackle. In my days at IBM, I've been working at using deep learning to solve some problems that existed there. So looking at tickets that were opened by customers when they had problems with DB2, I created a couple of models that would predict how long it would take for the ticket to get resolved, and whether or not the ticket would result in an escalation, whether there would be a duty manager call. So those were interesting applications, but obviously I could not publicize those data sets. This was information that was proprietary to IBM and to our clients at the time. So I needed to find an open data source that was big enough to be applicable to deep learning, but not too huge. I didn't want to get into the world of having to deal with some of the additional overhead of dealing with really, really large data sets. And I found in the city that I live in Toronto, the Transit Authority publishes a data set of streetcar delays. So this is the streetcar or tram network in Toronto, which is an important part of the public transit network. The Public Transit Authority publishes this data set, which records every delay that's happened on the network since 2014. And the goal of the model that's described in the book, the goal of the process is to train a deep learning model with this data set that will predict whether a given streetcar trip would be delayed. So that's the problem to tackle. Now, one of the things that was interesting but also challenging is that this data set was extremely messy. There were about 80,000 records at the time when I finished off the book. Will be over 100,000 now. The records are organized in a set of spreadsheet files. So there's one spreadsheet for each year, and within each spreadsheet, a tab for each month. But the key thing about this data set is it is extremely messy. So it was never intended to train a machine learning model. There was a reason why the Transit Authority collected this information, but whatever reason that was, it wasn't to make it easy for me to train a deep learning model with it. So this page highlights some of the problems that occurred. So for example, the direction that the streetcar was going at a particular time is key. It's a key aspect of the nature of the delay. And you think about, well, what would valid values be for direction? You say, okay, we've got 4, north, south, east, and west, and maybe 1 to indicate there was a problem in both directions. So maybe 5 values. There were over 15 different values. So different combinations, different ways that east and west were expressed. So that all needs to be cleaned up. The locations of the delays tended to be street junctions. So Queen Street and Broadview, for example. But the order of the streets was messed up. Sometimes the location was a landmark in Toronto. Quite often it was a landmark, not a generally known landmark, but a landmark that was very specific to the streetcar network. And then there were a number of months where the schema for the data set changed. So a couple of months where there were additional columns added to the data set, or the column names changed. So really the point of this is that the data set was a mess. It was quite challenging to get it to the point where it could be used to train a deep learning model. And the overall idea is to take that data set with all its flaws, with all its warts, take it through the whole process from cleaning up to creating and training the model to deployment, and show how all the pieces work together. Have all the code available in a GitHub repo, the data being open source, and lead the reader through the process of going from end to end. And I'm gonna step through the parts of this diagram just to provide a little bit more detail on what was happening technically at each of these stages. So the first step was cleaning up the data. So this was done. There's a single Jupyter notebook with Python. It used the pandas library. So pandas is, you can think of it as Python's library for tabular data. And there were a number of functions in there that would clean up the data set. So rationalize the directions, clean up the location information, deal with incorrect or ambiguous indicators of what route was affected. So basically going through each of the columns I was interested in and getting that data cleaned up. So the output of this notebook is a cleaned up data set, and it was saved as a pickle file. So this page just shows the before and after. So one of the other things that I needed to do, in addition to cleaning up the individual columns, this took a little while to kind of get my head around this particular problem. The original data set, all it had was the delays. So it had 80,000 records just recording delays. But really what I'm interested in is not just the times when there were delays, but also the times when there were no delays. So I needed to take that data set and explode it so that I was having for all of the possible combinations of a time frame, a streetcar route, and a direction, whether or not there was a delay, and include in that refactor data set records for when there was no delay. So that may seem like a relatively simple thing to do, but it was actually took me a while to understand this is something you need. The data set as it came in only told a part of the story. So the data is cleaned up and it's in a reasonable format. The next thing is sort of the meat of the whole process is creating and training the deep learning model and creating a pipeline. And what the pipeline does is it ensures that there is consistent preparation of the data when the model is being trained and when the model is being asked to make a prediction. So you can think of this as an example. One of the elements of the data set is what day of the week are we talking about? It's Monday, Tuesday, or Wednesday. And at a very simple level, deep learning model, machine learning models in general, can only be trained with numbers. So that Monday that was in the data set needed to be changed to a numeric identifier. And I need to make sure that if Monday was mapped to 0 when the model was being trained, that the exact same mapping happened when somebody wanted to use the model to see if there was a delay. So model mapped to 0 when the model's trained, or Monday mapped to 0 when the model's trained, Monday needs to be mapped to 0 when the model is being called to make a prediction. So that's the pipeline. And then there was the model itself. So I'm going to talk a little bit more about the model. And one of the key ideas in the book is for each of you can think of it as each column of the input table, the table that's used to train the model, is categorized to see, is it a continuous column? That is it something that's countable, like a temperature, a dollar figure, a duration of time? Is it a categorical column? That is it something that has values that are in a set that has less than 2,000 values in it. So for the streetcar example, an example of a categorical column would be the route. Which streetcar route are we talking about at a particular time? Or the day of the week. That's another thing that could be a categorical column. And then there are text columns, which would just be free-form text, such as a description of the nature of the delay. And what this image is showing is for each of these different classes of columns, a different set of layers was generated in the model. So for continuous columns, they just concatenate with the rest of them. The categorical columns are assigned, the values are assigned embeddings. They go through a number of other layers, and then they're concatenated. And then for text columns, there's a very simple LSTM-like approach taken for text columns. And one of the things that was interesting in this process is this really what the approach that it took to text columns, even at the time, so this was back in 2019 and 2020, was not cutting edge. It was an extremely simple-minded approach to dealing with text. And even with that simple-minded approach, it made a difference. Including the text columns would improve the performance of the model overall. But the architectural idea, the point of this is, if you have a tabular data set, look at the columns, categorize them, whether they're continuous, categorical, or text, and then assign a different set of Keras layers depending on what kind of column they are. And this approach, you could expand it to deal with other kinds of columns, like date columns, for example. In the book, I just covered these three. And this page just shows what the code looks like for each of these. So this is literally the code that builds up the model. And the idea is that this is done automatically. So once the columns have been categorized, the code automatically generates what the layers should be in the Keras model. Number 1 is for categorical columns. Number 2 is for text columns. And number 3 is for continuous columns. And this just shows in code in more detail what was on the previous page. And this is a picture of, and it looks complicated, but actually is relatively simple. It's a picture of what in diagrammatic form of what the model actually looks like. And the elements coming at the top, these are simply columns from the data set. So there is a column for the hour, year, and root, for the month, the day of the month, the day, and those all get fed in. They get combined, and the layers you see underneath them are depending on whether the columns are categorical, continuous, or text. And then you get a result out at the end. I mentioned the pipeline before. So in parallel with training the model, you need to train the pipeline. And the idea here is you get the raw input, it gets cleaned up and refactored, and then the categorical values get encoded. That is things like Monday getting assigned to 0. And that is trained so that it's consistent at training time and at the time when the model is being used to make a prediction. The book goes through, and when it sort of established, okay, here's the approach that's going to be taken to create the model, it goes through a series of experiments. And the idea of this is to sort of build it up in steps from a model with very poor performance to a model with better performance by making certain changes, either to hyperparameters or to other aspects of it. So one of the key things in this data set is the delays are actually quite rare. So the data set that had a row for each combination of a time slot, a route, and a direction, there are about 2.5 million rows representing all of the time slots back to January of 2014. Less than 2% of those rows represented delays. So delays are quite rare. So if all you do is just feed that into a deep learning model, it's going to predict no delay all the time, because it's going to be over 98% accurate. If it just predicts no delay all the time, it's going to be over 98% accurate. So one of the experiments layer in the idea, and Keras has parameters that you can control this to indicate that the data set is imbalanced to help correct for that. And another major thing is using callbacks. So what Keras callbacks let you do is make the training as efficient as possible. So if you don't use callbacks, you say, I want the training to go for 50 epochs, it'll just run to the end. And whatever you get as the trained model at the end is what you get. What that means is it's possible that after 20 epochs, the performance is getting no better. It doesn't matter, it'll run to the end. It may be that you have your best performance on epoch number 35, and then it gets worse. Doesn't matter, it just goes to the end. By using callbacks, you can stop the training once it stops improving, and you can ensure that you save the trained model that has the best performance for the epoch run. And this is important because there were a couple of approaches that somebody who's reading the book could take to run the code. They could run it in Google Colab, which is free, or they could use Paperspace, which has an hourly cost to it. And if you're using Paperspace, it literally costs you money that you're wasting if you don't use callbacks to control the training process. And this is something that while Keras is a fantastic framework, the idea of callbacks is a little bit, particularly for people who are beginning to use it, isn't really called to the fore. So I spent a fair bit of time in the book explaining why callbacks are important and why they really can end up saving you money by making the training process more efficient. So I mentioned XGBoost. So you can think of, if deep learning is Batman, XGBoost is the Joker in the context of dealing with problems in structured data. So I needed to actually address this. I need to say, well, people are going to say XGBoost will be better with structured data sets. So I knew that I needed to face this head on. And what I decided to do was take the whole code structure, so several thousand lines of code, and show an example where I've taken out the deep learning engine and pop in XGBoost. So the rest of the car stays the same. The data preparation, the deployment, all of that stuff stays the same, just changing the model. Now the good news is this was relatively straightforward to do. It wasn't a ton of coding work, and the results were interesting. So comparing the performance of trained model using deep learning with XGBoost, I looked at it at 4 different categories. The first is overall performance of the model. The second is the training time. The third is the code complexity, and the fourth is the flexibility. So on the first one, I have to give it to XGBoost. XGBoost did produce slightly, not hugely, but slightly better accuracy and recall on a consistent basis. So just out of the gate, XGBoost had slightly better model performance. The training time was roughly the same. The deep learning training time was more variable, but it wasn't a huge difference between the two. For code complexity, there were a few more lines in the deep learning structure, but I'd say it was more transparent. Whereas XGBoost is, to a certain extent, a little bit more of a black box. You call the API and you get the results back. Whereas with the deep learning model, you see what all the layers are. So I'd say that was kind of inconclusive. So where did deep learning shine here? It's in flexibility. So with deep learning, you could have an input data set that had a column that was free-form text. So for example, if you're running an e-commerce site, you could have a column that has a description of an article of clothing. So it says what the clothing is, has some kind of marketing description around it. That could be easily fed into a deep learning model. It would be quite a challenge for XGBoost. You may end up having to have a deep learning model on the side with XGBoost. Similarly, you could have large objects with images in them and incorporate that directly into a deep learning model. So the flexibility, the ability to deal with a very large gamut of structured data sets, deep learning is the winner on that side. So we've cleaned up the data set, we trained the model and the pipelines, and now it's time to do deployment. And for deployment, I looked at 2 different approaches. The first was web deployment. And this is using a Python library called Flask. This is a very simple Python library for web applications. So the code that accompanies the book includes everything you need, the web pages, CSS files, as well as the Flask server module to serve a set of simple web pages that deploy the model, which allows somebody to go in and say, this is the streetcar route I want to take. This is the direction I want to take. This is the day I want to take it on. And you get back a prediction from the model. And this page just goes through the details of how that works. And I really wanted to, there are cloud deployments available for deep learning that abstract a lot of this detail. And I really wanted to make a point of going through this because it's something I think, both because a lot of training about deep learning just completely skips over deployment, or it makes it entirely a black box where you don't see any of the details. I really wanted to make sure that it was transparent. People could see, I've trained the model and this is exactly how it gets deployed. This is how somebody could practically use it. Now, in a real production deployment, we wouldn't do this. This wouldn't be the approach that's taken. But as an end-to-end picture of how this could be done with a web application, it certainly shows that. Now, somebody's not likely to want to go to a website. If they say, I have to get to work and I want to know whether my streetcar is going to be delayed, they're not likely to go to a specific website to enter a bunch of data to see if their streetcar is going to be delayed. So in addition to the web deployment, the book also covers a deployment in Facebook Messenger. And what this means is you have a chatbot that you can say, I'm taking Kingston Road route east. Will it be delayed? And get a prediction back directly with that. So a much lower, much easier way to interact with the trained model. Now, the stack that makes this up is more complex. So it involves the open source Rasa chatbot framework. And that's used to take the English language input that somebody would put into the chatbot and pick out of it what question is being asked. So they may say, I want to know if Route 512 is going to be delayed, or I want to know if the Queen Street car is going to be delayed. I want to go north, I want to go northbound. So all of those different variations in the English, what Rasa does is allows you to pick out with the intention of that request. And then that can be used to get the values that are fed to the trained model to come back with the prediction. So this involves the data going through. So here's an example. Somebody would put into the chatbot, will Kingston West be delayed? That gets captured by Facebook Messenger. It gets sent to Rasa, which has a Python backend, which fills in the details about the request. It runs those details through the pipeline. It calls the trained model. It gets the response back, the prediction back from the model, and that gets sent back to Facebook Messenger and gets displayed in the chatbot. So a very simple experience for the client, but quite a bit more complex behind the scenes and involving Rasa, which is a sort of another level of technology that wasn't involved with the web deployment. Now, the interesting thing about Rasa is that it uses that, when I talk about it does, you can get it to do interpretation of English language text to pull out the key elements, like what's the intent, what's the person trying to say. It is using a deep learning model there as well. So this deployment, the Facebook Messenger deployment, has deep learning to predict whether or not the streetcar is going to be delayed, and a whole different deep learning structure to interpret the English language request that the user makes to determine whether or not their streetcar is going to be delayed. And that is the from the raw data set to the deployed trained model. That's the end-to-end picture. I just want to check, are there any questions in the chat right now? Pause for a moment.
I think there are no questions so far, but if anyone wants to ask anything, feel free to type in the chat.
Okay. Well, I will keep moving on. So this approach covers a broad variety of technology, but it's also very, in some ways, it's the minimum viable product. It's simplified in a lot of ways. And there are a number of enhancements that could be made to make the model more accurate and to improve its performance. So the final chapter of the book goes through what some of these enhancements are. One is to add geospatial data. So to use to take the locations of the delays, turn them into latitude and longitude values using Google's geocode API, and then do various things with that. For example, you could take a streetcar route and cut it into subsegments. So instead of saying, will my trip on Queen Street eastbound be delayed? You could say, will my trip for a particular section of the Queen Street eastbound be delayed? Another thing is weather data. So Toronto can have some severe weather, particularly in the winter. And there are APIs for weather data. You can get weather data historically. So you can use that as part of the training process and get real-time weather data. So adding weather data may add to the accuracy of determining whether or not a streetcar is going to be delayed. And then there's some sort of ML ops improvements that could be made, automating the code flow. So right now there are certainly manual steps in the end-to-end process. The code resides in a set of different Python modules and Jupyter notebooks, and automating that is something that would be interesting. And incorporating Docker. So using more kind of a cloud-based approach for deployment would be something to be interesting as well. And finally, applying the same approach to other data sets. So for example, the Transit Authority in Toronto also publishes a data set of subway delays. And that's a different set of problems. The streetcars are running on public streets, so they're affected by accidents. They're affected by weather. The subways are, for the most part, underground. It's dedicated, but there are other issues that can cause delays there. So that's an interesting potential future approach, is to see, could the same approach be applied to a different data set. And in fact, I'll talk about this a little bit. So on this page, we've got links to 3 things I've worked on related to this topic. The first is the book, Deep Learning with Structured Data. So that goes through what I've been talking about, the end-to-end process from a raw data set to a deployed, trained deep learning model using the Keras framework. Once I finished the book, I also worked with Manning on a live project. And this is it's a set of interactive coding exercises. So it's using the same approach as the book, but a different data set. So instead of the streetcar delay data set, it's a data set of Airbnb listings for New York City. And the goal is to train a model that will predict prices for Airbnb listings. And this demonstrates the flexibility of the approach, because the code largely works with minimal changes between the streetcar data set and the Airbnb data set. And it also introduces some different kinds of data, in particular geospatial data, because the Airbnb data set has for each listing the neighborhood as well as the latitude and longitude for the specific listing. And then finally, I wrote a book. This is for a different publisher, for Pact, on the Fastai framework. So Fastai is another high-level deep learning framework. Keras is the high-level deep learning framework for the TensorFlow. And Fastai is one of the high-level frameworks for PyTorch. So PyTorch and TensorFlow are the 2 major overall frameworks for doing deep learning. So the Deep Learning with Fastai cookbook goes through exercises for using Fastai to create simple deep learning models that deal with image data, with recommender systems, with text data, and with tabular data. And the interesting thing about Fastai is it has a full structure to deal with tabular data. So tabular data is a first-class citizen in Fastai. And there's a whole chapter in the Deep Learning with Fastai cookbook that shows how to use Fastai to train deep learning models on a variety of different tabular data sets. So it's looking at the same kinds of problems as the Deep Learning with Structured Data book and the live project, but with a different framework, with the Fastai framework. And here, there's more resources. So there's a link to the book site, a link to the Fastai course. And if anybody is interested in getting into deep learning, if they say they want to kind of get their feet wet and understand it, I couldn't recommend anything more than the Fastai course. It does a fantastic job. It's very practical. It emphasizes getting results. It does cover the theoretical aspects of deep learning, but it's really focused on helping non-specialists to get enough skills with deep learning to be able to solve problems in their area. There's some examples here of research. I mentioned before that there's only been limited research on deep learning, but I have some links here to a paper on a particular approach to deep learning with structured data, as well as a survey of recent papers on the topic, and 2 excellent video overviews. The first one there is by Luca Masseron, who's done some fantastic work. Extremely practical, very, very useful, and very encouraging for somebody who's interested in deep learning with structured data. The work that Luke has done has just been really encouraging. He's done great work, and that video I highly recommend. And then I encourage you to connect with me on LinkedIn and the YouTube channel, which covers a number of deep learning with structured data topics, as well as using some of the breakthroughs I talked about earlier. So there are videos on using OpenAI's GPT-3 and Codex, as well as videos about Fastai. A link to my Medium blog area, a link to my repos on GitHub, including the repo for this book, and connecting with me on Twitter as well. And that is everything that I had prepared to cover today. So let's see what we have in terms of.
Perfect. Thank you, Mark. That was a great presentation. I think we have quite a few questions. Some are more like high level, some others are a bit more technical. The first one is by us, who asks, really interested in how predictions fare with real world situations.
So the for the streetcar model, the performance at the beginning of 2020 wasn't bad. It was between 75 and 80% in terms of its ability to predict whether or not a particular streetcar trip would be delayed. Now, then something major happened in the world starting in March of 2020, and the data set became very different. So the traffic patterns in Toronto changed considerably due to COVID. I haven't retrained the model with the most recent data, but I would expect that COVID would, that data, if I incorporated all the data from the last 18 months, it would probably not have a positive impact on the accuracy of the model.
Perfect. The next question is this used, can this be used to reduce delays or just predict whether a delay will occur? But I guess these two are kind of tied together, right? They're not independent.
Yeah, that's a great question. So the intention, the audience for this model is the customers. So it's to say, do I know, is my trip going to be delayed? I did share this with the transit authority. So potentially they may decide to take advantage of it. I think there is some use to be able to use it to prevent delays, but right now the model, the way that it's created and the way it's deployed is not for the transit authority to prevent delays. It's for individuals who want to take trips to be able to know whether or not that they should get on the streetcar or get an Uber or a taxi or walk.
Then our friend Zane asks, because he missed the first part of the presentation, whether you needed any big data infrastructure like Hadoop or Kubernetes. My understanding is that you didn't need any of those things, right?
That's right. Yeah, and this is something I think, as you saw, I showed the schematic of the architecture. Going from end to end, it was already relatively complex. So I particularly looked for a data set that wasn't so huge that I need to look at some kind of distributed approach like Hadoop. And then in terms of deployment, I wanted something that somebody could deploy without having to use a cloud environment. Now, an improvement I would like to make, I mentioned that in the context of the future improvements, is to cover a cloud deployment, and that would by default involve Kubernetes. Now, for AWS and Azure, Google Cloud Platform, Kubernetes is there, but if you're deploying, if you come with your model and deploy it, usually you wouldn't need to worry about the details. So you shouldn't have to worry about the details of Kubernetes. It should be something that you can say, this is the model and I want to have it deployed, and that's abstracted to a certain extent. So short answer is the book doesn't talk about Kubernetes or Docker, any kind of containerization or cloud deployment, other than mentioning that it's one of the options that somebody could have.
Another question is, someone says that when they try deep learning or structured data with categorical features, they face issues with memory when they try to create embeddings, because that's a very technical topic, but I don't know whether you know of any techniques that can help around reducing the memory.
What I recommend is the first, in the page of references, the first video I point to, it's Luca Masseron's video. That does cover this topic. So my book does not cover this topic, but Luca does talk about the issue of categorical columns with a very large number of values in them. So that may be useful. Perfect.
One more question that's fairly technical by Akash. I don't know if you can see it. It asks how the algorithm accounts for the longitudinal data structure and something around repeated observations.
So I'm not sure if I completely let me read the question again.
Yeah. Yeah, I think that's the last question for this session, actually.
Okay.
Yeah. Did you find the question?
Yeah, I do. Yeah, so the question is, since the streetcar data structure has repeated observations on a streetcar, for example, Route 504, how does the algorithm account for this longitudinal data structure? What needs to be kept in mind with such repeated observations, since the same route may be observed at different points in time? So I think, if I'm interpreting this correctly, the question may be about whether the original data set would have multiple, for the same delay, would have multiple rows based on the same delay. I'm not sure if that's a correct interpretation of the
I
question.
think that's quite what he means.
Yeah, so that's the short answer is that's not something that I dealt with. Looking at the data set, and obviously with 80,000 records, wasn't able to check every instance of it. But having some understanding of how the data set was collected, the observations would tend to be distinct. That is, a single delay incident would only have a single entry in the data set. Now, that isn't to say that there aren't some cases in all 80,000 records where the same delay gets reported multiple times, but I don't think, based on the other ways the data was recorded in the data set, I don't think that was an issue in this particular data set. And it may have just been lucky that way. So it wasn't intentionally putting in something to avoid the problem. It was a bit of luck. So while the data set was very messy, I don't believe it had that particular characteristic of multiple reports of the same delay.
Perfect. So I think this was the last question. So for everyone who's asking about the slides, yes, we will be sharing them after the presentation. And also there will be a recording of that video of this presentation on the datascientist.com. Again, if you want to buy the book, here's the link to the Manning website. And here's also a link to Amazon. And yeah, big applause for Mark. Thank you. This was an excellent presentation. And I'm sure that everyone who buys the book will find it very useful in their data science practice. And thanks everyone. Make sure to also join us on Eventbrite or on Meetups, Data Science London on Meetups or on Eventbrite. Simply look for Beyond Machine to learn more about these and similar events. And we hope to see you again soon in some other of our free events around data science, deep learning, and related topics. Thanks, everyone. Have a great rest of the day or evening, depending on where you're located. Thank you, Mark.
Thanks very much, everybody. Thank you so much. Thanks. Bye-bye.